Welcome to lecture number 9 of digital signal processing. In this lecture, we are going to cover the sampling theorem, and then we will move towards the second step of analog to digital conversion, which is quantization. We will see that what are the possible techniques to quantize any signal, and how quantization introduce an error in the signal, and we will discuss some general terminologies related to the quantization. Then after that we will move towards the encoding step, which is the third step of analog to digital conversion. So we are going to actually sum up our analog to digital conversion in this lecture. So it is quite interesting that we have to select a correct sampling rate in order to our signal to be sampled correctly, so that we can reconstruct our signal accurately. So for this sampling rate, there is a criteria which is generally and very famous criteria, which is generally known as Nyquist criteria, or you can say it as a sampling theorem. So this theorem actually tells us about that what rate would you select for sampling any signal. So generally speaking, we have some information about the nature of signal we are going to process. For example, if we are processing a speech signal, then we know that it is a speech signal. However, we do not know the actual frequency contents which are present in that signal, but in general we know that okay, it is a speech signal. Or in other case, if we are going to process any ECG signal, then we know that what the signal we are processing is ECG signal. We do not know the actual information signal is carrying, but only we know the nature or characteristic of that signal. And actually the purpose of processing of signal is usually to extract the detailed information. So at this stage we do not know the detailed information, but we know the nature or type of signal. Either it's a speech signal, it's a brain signal, it's a video signal, or maybe some any other type of signal. So in this case we already know that okay, this is a speech signal, then the maximum value of frequency which can be present in that signal is around this much frequency. And if we know the value or the value of the maximum value of frequency which is to be present in that signal, we can do the sampling very accurately by using this theorem. And this theorem states that f max must be fs, which is the sampling frequency, must be greater than or equal to the twice of f max. That is actually what the formula is telling us. Whatever the maximum frequency which is present in that signal, multiply it by twice, then whatever you will get the result, set this value as your sampling frequency, either this value or value greater than this value, because the sign is greater than or equal to. If you use the same value or equal, which is equal to 2f max, then you will face no difficulty. But if you are increasing the value from twice of f max, then you will get more accurate sampling. More accurate sampling means a more precise results. But again, if you are increasing this sampling frequency, then you can understand that you are actually increasing the number of samples, or you are increasing your sequence which is to be processed by some processor. And if you are going to process larger sequence, then it will consume more time, or either you have to use a very smart and very speedy gadget or processor to process this large number of sequence. So basically it is a trade-off that how much frequency or sampling frequency you are selecting, but the criteria is at least you have to select twice of f max, whatever the maximum frequency which is to be present in that signal. And from where you will get the idea? You will get the idea from the nature of the signal. If it is a video signal, you know that it will comprises of the frequency up to 5 megahertz, then okay, 5 into 2, 10 megahertz. I may select the value of sampling frequency of 10 megahertz, and if I select sampling frequency more than 10 megahertz, it will be more better. So I hope you get the idea of sampling theorem. Now we are moving towards the second step of analog to digital conversion, which is quantization. As you all know that continuous time signal is converted into discrete time signal by processing through three steps, which are sampling, quantization, and encoding. And in the first step, which is sampling, we have discretized the time axis, or in general we can say the x-axis. So now in the quantization process, we are going to discretize the y-axis. It means we have a discrete time but continuous amplitude signal as an output of sampling, and we are converting that discrete time continuous amplitude signal, or we can say discrete time continuous value signal, into discrete time discrete valued signal. That is, DTCV signal is to be converted into DTDV signal in this process, which is known as quantization. As we have already discussed that quantization is the irreversible process, and it always inject some noise or distortion in the signal, because we have to represent our continuous valued signal by finite set of discrete value levels. So an error, or we can say noise, is introduced in the signal, and that error or noise is known as quantization error or quantization noise. And if we want to represent this quantization error or quantization noise mathematically, then we can say that it is the difference between the quantized value and the actual sample values. That is, we have suppose we have a block of quantizer, and we have some input to it and output to it. So the input is unquantized signal, and after passing through this quantizer block, this signal is converted into the quantized signal. So previously we have actual values, and after quantizer we have the quantized value. So the quantization error or quantization noise is basically the difference between these two values, that is quantized value and actual sample value. We will learn the actual mathematical relation in later slides. In this slide, we are actually going to learn the quantization process and the terminologies associated with this step of quantization. So moving forward, in this slide we have a signal, and if you say that in this slide we have actually a continuous time signal, which is then discretized along x-axis, and then you can also see that we have different levels at the y-axis also. So let's begin with the very basic signal, which is the continuous time and continuous valued signal, which is analog signal. So analog signal in this plot is represented by xa of t. You can see the position of pointer. I am indicating the analog signal. This is basically the analog signal or continuous time continuous valued signal, and it is represented by xa of t is equal to 0.9 t. So you can see that this function exists for every value of time as well as infinite values of the amplitude, that is y-axis. So when we discretize this signal, or we can say when we sample this signal and we choose this sampling frequency as 1 hertz, so it is a periodic sampling or uniform sampling. So time interval is fixed, which is the sampling frequency, and frequency is selected as 1 hertz. So after each 1 second we are going to take this sample of this signal. After performing uniform sampling, we will get the discrete time sequence or discrete values indicated by my pointer, that the first sample is at n is equal to 0. This one is the first sample. After time interval of 1 second, which is the sampling frequency, we will get another sample, which is this one. The third sample as n is equal to 2, fourth, and so on. So you can see that this analog signal is now converted into a discrete time signal. Now in this quantization process, we have to convert actually this discrete time signal into discrete valued signal also. You can see that if we compare both the values, that the continuous time value and the discrete time value, then at n is equal to 0 we have value 1, because 0.9 raised to power t is raised to power 0 is 1. And when this signal is converted into the discrete time signal, then the expression becomes x of n is equal to 0.9 raised to power n, because t is converted into n for all values of n greater than and equal to 0, because this function exists for the positive values of n and not for the negative values of time, neither for n. So this is the expression for continuous time signal. And if we talk about the expression of discrete time signal, then this expression becomes x of n is equal to 0.9 n. So when we put different values of n in that equation, then we will get these sample values. So what is actually going in the quantization process, we have you can see from the n is equal to 4, that is fifth sample. It is clearly seen from this sample that n is equal to 4. We will get this sample value which will collide with the actual analog signal, because we already concluded that sampling does not introduce a distortion in the signal. Whatever the actual value of signal is, the after sampling we will get the same value. So if we look at the values for the signal, then you can also calculate when we put n is equal to 0, then we will get the value of 1 for n is equal to 0, which is plotted like this. For n is equal to 1, we will get 0.9 plotted at this point. For n is equal to 2, we will get 0.81 fairly marked here at 0.81, and n is equal to 3, we will get the value of 0.729 marked here, and so on. But for n is equal to 4, we will get this value. But in the quantization process, we are not free to choose any values, but we have to choose only between the finite values, set of values, and these finite set of values are indicated by these horizontal lines. That is, we can either choose from 1, 0.9, 0.8, 0.7, 0.6, 0.4, 0.5, and so on. So here what's the value is 0.65 something, but in actual we are mapping it at 0.7 because we have no value or no choice to select the value between 0.6 and 0.7. If we have a choice, then we have to increase the number of levels. You can see from the plot, if we increase the number of horizontal lines, then we can actually choose the more possible values. So you can clearly comment by looking at this graph that if we are going to increase the number of quantization level, these are basically the quantization level as indicated in this plot also, levels of quantization by horizontal lines. You can see my pointer, this is level of quantization is basically these horizontal lines. So you can increase these number of levels, but again if you are increasing this quantization level, then you are actually increasing the cost of the converter, and on the other hand you are also increasing the complexity of the converter. It means it will take more time to process the signal. So what we will do with this, we will discuss it in the later slide, the what's the trade-off will be and how we can select these quantization level. But you can see that this quantization always introduce an error because the actual value of signal is something different, and you have to choose between the available set of samples which may not be equal to the actual signal value. So this signal actually mapped, or this point is actually mapped at 0.7. How we are mapping this at 0.7? Why we not mapped it at 0.6? So it's another discussion. Basically what happens, we have several techniques to do quantization. If you look at the actual value at sample n is equal to 4, then the actual value will be 0.6561. If you calculate, if you use your calculator and put x of n is equal to 0.9n and put 4 at in place of n, so you will get 0.6561 value for this sample, which is at n is equal to 4. But if we look at the quantization level, we do not have such value in the available quantization level. We have to either choose 0.7 or we have to either choose 0.6. Alternatively, we can develop another scenario for our understanding. Suppose you have a function as written as 0.9 of t, and after converting it into discrete time signal, it will become 0.9 of n. And if you calculate the function values for different values of n, then you will get, for n is equal to 0 you will get 1, for n is equal to 1 you will get 0.9, for n is equal to 2 you will get 0.81, for n is equal to 3 you will get 0.729, for n is equal to 4 you will get 0.6561, for n is equal to 5 you will get 0.59049, and so on. So if you look at these values carefully, then you will notice that number of significant digits are increasing as we are moving from 0 to later number of samples or higher number of samples. So you can also think that, okay, first value is 1, then 0.9, then 0.81, then 0.729, then 0.6561. Digits are increasing, and if you are going to process this type of signal, actually digits are basically representing the signal. So if you are going to process this signal, you can maybe you are developing some filter, or you want to extract some other information from that signal. So actually what you have to do, you have to process this signal, and you will, if you want to process this signal with any digital computer or digital processor, then there you will have finite memory. And if you are using finite memory, you cannot use infinite significant digits. You must limit your samples to certain specific number of significant digits. For example, you may say you can adopt 3 digits and omit the higher digits or the other digits. So you have to set some limit to select the number of significant digits. So this selection can be done by using various techniques. You can use the rounding of formula, you may apply the truncation technique, you may also use the floor technique, flooring the value, or you may use the seal value for that sample. So there are different techniques to convert that values which may be non-terminating into finite number of significant digits, which may be 2 or 3, and these 2 or 3 digits can be represented by finite number of quantization level. You will not need infinite quantization level if you limit your figure to some certain number of digits of or number of significant digits. So this is basically the quantization is. If you look at the plot, then you will find that the plotted sample values is actually by the rounding of technique, that is 0.7, n is equal to 4, we have value 0.6561 and it is mapped at 0.71 by using the rounding of technique. So we can use any other technique also, but this plot is plotted by using the rounding of technique. So by focusing on this discussion, we came to know that there might be several terminologies associated with this quantization process. So first one we have already discussed, which is the levels of quantization, that are the horizontal lines, or you can say that finite values of samples from which you have to select and map your original signal. Or you can also say that values allowed in the digital signal are quantization level, and the difference between two quantization level is basically the resolution, which is denoted by the delta. You will see the actual formula in the later slide. So you have learned the quantization level, resolution, which is the quantization step, and the third thing is the range. Range is actually the how much your signal is varying, that is the least value of the signal along the y-axis and the highest maximum possible value of the signal along the y-axis. So this will form the range of the quantizer. So here in this slide you can see the values which we were talking about. We have different values for n, and the x of n values are given for different values of n, and after quantization what values we will get. Quantization we can choose the truncation technique. The third column is basically for truncation, and the fourth column is when we choose the rounding of technique. So you can see that n is equal to 4. At n is equal to 4, we will get 0.6561 as actual discrete time signal, and after the quantization process, if we will do quantization with the help of truncation, it will give us zero point 0.6, and if we will select rounding off, then we will get 0.7. So neither the zero point 0.6 nor the zero point 0.7 are the actual values of the signal, but these are the manipulated values. Actual value is 0.6561. So I hope that it is clear now that quantization always introduce distortion in the signal, because we do not have every value, we cannot have a possible set in which every value of our actual signal is present. And if this happens, then it will not a discrete valued signal, then it is normally a continuous valued signal. So, and one more interesting thing you can note, that after quantization we will have some error in the signal, and this error may be 0 if we have the same value of actual signal and the same value is present in the sample set from which we have to chosen the value, and this rounding off maybe have, or this quantization maybe have error have another value. So if we talk about rounding off, then we will get these error for the rounding off quantization process when rounding off technique is used, and you can see that the magnitude is varying from n is equal to 0 to n is equal to 9. But what is the maximum value of error we can have in a signal? A question may come in your mind that we are actually quantizing the signal, and we know that it is a irreversible process and we will have some error in the signal, but what will be the maximum value of error we have to face in our signal? So the answer is quite simple. Quantization error, if we are using the rounding off technique, is limited to the range minus delta by 2 to delta by 2, because the resolution is delta and either value is mapped at the higher level or the lower level. So the maximum value of error is from minus delta by 2, which is delta is actually the resolution. So the error will be the minus delta by 2 to delta by 2. Other terminologies and mathematical relationship for associated with the quantization step is the dynamic range, and dynamic range is actually the maximum value of x, which is the signal, and the minimum value of signal, or you can say minimum value of quantization level. So x max is the maximum value of quantization level and x min will be the minimum value of quantization level. And resolution, or you can say step size, how you can determine the step size. So here it is the formula x max minus x min, which is the dynamic range, divided by L minus 1, and here L is the number of quantization levels. And how you will determine the number of quantization level? So to determine the quantization level, formula will be L is equal to 2 raised to power n, where n is the number of bits. If you are increasing more number of bits, so you have more number of quantization level, and more quantization level means quantization error will be minimum. Quantization error will be minimum means your signal will be more accurate. More accuracy means cost of the equipment is greater. If you use the lesser number of bits, so cost of the converter is cheaper, and if you use the higher number of bits, so your converter will be of higher cost. Here we can see another example in which we have quantized. First we have sampled and then quantized an analog sinusoidal signal, which can be generally represented by A cos omega t, and we have plotted the curve, and we have make the grid lines on to compare the actual analog curve and the digital curve. So you can see that horizontal lines basically are the quantization level and vertical lines indicates the sampling time. So the actual signal is xa of t, which is analog signal, and from this signal we have obtained a discrete time signal, which is represented by x of n, or you can say xa of nt. So xa of nt is obtained by sampling, and sampling actually did the discretization of time axis, and discretization of amplitude is obtained after the quantization. So, and after this process, you can we also join these samples, so you will see the staircase signal, and staircase signal is basically you can see that it is a digital form of signal. So this type of signal is normally obtained by using zero order hold circuit, which means that to retain the previous value of sample until next value is achieved. So this is actually zero order hold circuit. So this staircase is actually obtained by using the zero order hold circuit. Uh, just see at this figure, this is the sample and this value is retained until the next sample is achieved, and when this next sample is achieved, this next sample values is retained until the next sample is achieved. So this is actually the sample and hold circuit. Now moving towards the last step of analog to digital conversion, which is actually encoding of signal. So this encoding is basically assigning unique binary numbers to each quantization level. We have seen that in quantization process we have several quantization levels. So in this coding step we are actually assigning unique binary number to each level. So by doing this, each quantization level can be represented by different combination of binary numbers which are very unique to each other. So the formula is very simple. If you are using n number of bits, then the number of quantization level, if you assume L is the number of quantization level, then by using n number of bits you can achieve 2 raised to power n number of quantization level. It is very clear that if you increase the number of bits, then more possible combination will be there. If you are using 2 bits, then you will 2 raised to power 2 is 4, and then you can sample, you can quantize your signal only at 4 levels. But if you are using 3 bits, then you can quantize, then you can encode your signal, or you can first quantize your signal at 8 different levels, because 2 raised to power 3 is 8. So it means by using the number of bits you are actually the increasing quantization levels, and if you are increasing quantization level, it means you are increasing the accuracy of analog to digital conversion, as the value or the sample value or the amplitude value, you can say, is more closer to the actual signal value because more number of quantization level. So we have different analog to digital converters. Some have 4 bits to represent the quantization level. Some use 16 bits to represent the quantization level. It again depends upon the application, which application is you are performing this task, for which application. So by using the information of that specific scenario, you can select your analog to digital converter. But in general you can say that higher the sampling speed, which is the first step, or you can say the sampling rate, higher the sampling rate, and the finer the quantization, which is the second step, quantization, more number of level. If you are increasing these two things, that is higher sampling speed and finer quantization, then your analog to digital converter will be more expensive. I hope that these 3 points and these 3 stages of analog to digital conversion are clear to you. So students, in this lecture we have covered our analog to digital conversion process. I would like you people to review all the three lectures of this week, and I would like to you people to search some examples or real-time scenarios in which you have observed this analog to digital conversion. I have some interesting phenomena which I will inshallah discuss it with you in the live session with some uh, interesting videos. So try to gather some questions and try to extract some interesting phenomena based upon this sampling, especially aliasing and quantization and encoding of the signal.